Hi everyone, and welcome to Erik's Electronics Workbench. On the bench today we have this DC to AC 300 watt power inverter that has developed a problem and stopped working. So there's no output voltage and it just sounds the alarm all the time. It also tends to draw a fair amount of current and then it cycles and shuts off, but there's no output, no AC output, and the little internal buzzer alarm speaker just sounds off all the time. So I've already disassembled it. You can see the internal pieces all sort of come out as one assembly. These are the end panels. You have the input jacks over here, input connectors, fan, the fuse, the main circuit board of course, and then the other end panel has the AC outlet, two LEDs. This has a USB port for a convenient 5-volt output, and the main power switch over here. So everything slides into the main housing, which acts as a heat sink. So this is actually the bottom. It has a metal panel or cover that goes on the bottom, so it sits this way, when it's in use. So again, there's no output. The buzzer sounds all the time. I'll hook up the 12 volts to it and you can hear and see exactly what it's doing. While it's sitting here, just prop this up a little bit here, you can see the general layout. Zoom in a little bit closer here. So basically the DC, 12 volts DC comes in over here, comes down to a couple filters, inductors right here. The 12 volts is switched by, these are probably MOSFETs right here, and these switch the 12 volts at a very high frequency, and they drive this transformer. The transformer is small. Again, this is 300 watts. So it's 300 watt rating on this transformer, but it's made so small because of the high frequency switching. Basically the same idea as a switch mode power supply, where the switching is done at a very high frequency compared to 60 hertz where you would have a huge transformer. I have a 300 watt power inverter that uses traditional just 60 hertz switching on the transformer, and it's massive and huge, really heavy, so much smaller because of the high frequency switching. So the output of this transformer also steps the voltage up, so we have 12 volts at a high frequency going in, and the output is a high voltage. It's rectified by these 4 diodes, some filtering with this capacitor right here. The top of the capacitor, they have some heat shrink over it, and it looked like this when I opened it up. I don't know the heat shrink, it looks a little ragged on the top, but I don't know why they put heat shrink on this capacitor. I don't know if they're trying to insulate it or what was going on there. So anyways, the output, now we have a high voltage DC over here. This DC is applied to these 4 transistors, again probably MOSFETs, power MOSFETs over here. These are likely configured in an H-bridge configuration where 2 of them are on at one time and then the other 2 are on at another time, and basically your load, the AC output, is between the 2 pairs. So the effect is that you have the constant DC voltage being switched in one direction through the load and then in the other direction through the load, and that's exactly what AC 60 hertz AC sine wave is. That's what you want, is that the voltage is positive, then the voltage switches to negative, and that's how it's done generally, is with an H-bridge configuration. So the output of this H-bridge is fed through these 2 inductors over here, and we have 2 capacitors. This filtering over here ends up forming the true sine wave output that this inverter has, or is at least rated to have it. They do mention that it's a true sine wave. If it's not a true sine wave, the other style is, it looks like a kind of a square wave with a step in it. Not as good of a design when you have an inverter like that. It can cause problems with certain devices. A true sine wave output basically mimics the type of voltage that you would see at your wall outlet in your house or off of a generator or something like that. So after the filtering, it just comes over here. There's a little fuse down here on the circuit board, and the 120 volt receptacle right here. This is just a ground wire, these 2 hooked to a screw terminal on the inside of the chassis. So let me hook up the 12 volts, and you can actually hear the buzzer going off, and basically just confirm that it does in fact still have the problem now that everything's been opened up. I didn't see any shorts, circuits, loose wires or anything like that. The bottom of the circuit board looks clean. There were no issues with any of the traces. I've already looked at that. I don't see any open solders or burned traces or anything going on like that. Nothing visual that looks faulty. These sort of gray square looking things here are thermal insulators that are over the TO220 devices. They're kind of stuck on there. This one I got to come loose, so you can see it just comes off like that. But some of these, they're kind of stuck on there. They don't come off very easily. But you can see this is just a traditional TO220 style transistor or MOSFET. So these are just insulating the transistors from the heatsink or the outside of the chassis when it touches. These little metal bars right here span across, so they basically have a screw that comes in and it's a clamp, and these are squeezing these against the side of the case to make the thermal contact. So, put that back on there. Grab my power supply here. All right, the switch is turned off. You can hear that there's a problem there. Actually, the switch was on already, so you can hear that's, switch it that way. So, clearly a problem. It doesn't do anything other than just squeal, make a bunch of buzzing sounds there. The green LED is on over here, but it flickers. Basically, it doesn't really know what to do. There's definitely a fault. So, knowing all of that, let's take some measurements on the circuit board and see if we can get an idea of where the actual problem is. And what we'll do, put that up there. So we can get everything in the shot here. Now this, since we just powered it up, we want to make sure that there's no voltage on that large capacitor. Back this out a little bit here. Get that so there isn't the glare on the screen. I think we can see that there. That looks good. So that capacitor is across these traces. We're in DC volts. So nothing there. So that didn't store any charge, or it was already bled off. All right. See these traces here that have the extra material on the trace, you know, for the higher current where it flows in. This is a 30 amp fuse, so there is some fair amount of current that flows when this is working at 100% load. That had a little bit of a voltage on there, and then it's just sitting at 4 volts right now. This. Just short that, get that charge off of there. We don't want any charge on any of the traces. It would affect the ohm meter reading. If we try and take a reading for resistance or continuity and there's a charge, it'll definitely cause a problem. So that's got that bled down. It'll probably continue to discharge. So I don't see, when we hook up the DC voltage, the 12 volts, there's not an excessive current draw immediately. When you turn the switch on, it does tend to draw some current, and then it sort of shuts off. So I think it's detecting that there's a high current, and it's not a dead short on the input side. I know that because it seems to be detecting excessive current, and it's sort of like it starts to turn on and then it shuts off, starts to turn on and shuts off. The LED light, the green light on this end panel over here is kind of flickering, just gives me the feeling that it's trying to turn on and off. So I'm going to actually start on the output. We'll take a reading over here for any short circuits, and then we'll sort of work back through the circuit. Because if there's a short in the output somewhere, then you know, it would be like having a short across the load. It would basically shut down. So let's go over here to the ohm setting. So on the AC outlet, these 2 orange wires come over here to the circuit board right here. So, okay, already we're seeing that doesn't look too good. We got 1.1 ohm. If the leads are shorted on the meter, it reads about 0.2 or 0.3. So almost a dead short right there. That sure doesn't look right. Okay. Well, let's see here. So already we've got, looking under here, this across here to here on the circuit board is a capacitor. And of course this, there's an inductor between here and here. That's this inductor underneath right here. Okay. So that should have continuity. That does. You can see that continuity is actually a little bit lower, so that comes right at 0.3. But if you go across 1 point, so there's a slight resistance, but very low. I mean, that shouldn't be that low at all. See, that goes through over there. We know that these output transistors, these 4 right here, are switching to the load. So they could be suspect, but we could have a capacitor over here that's shorted. Let's see. Let's measure across. This is the filter, that large filter capacitor that's on the other side under here. Right, this one right here. See what we have across that filter. Geez, it's a dead short across that capacitor. Now that doesn't mean that capacitor is faulty. I mean, maybe it is, but again, a component in that circuit could also be shorted, and you know, the reading just happens to be, you know, that we're taking it across this capacitor, but it may or may not be the problem. But I mean, that is really, really dead short in the circuit somewhere here. These are, I believe, the diodes right here. There's four rectifier, power rectifier diodes right there. Let's look just in general around those and see if anything looks shorted. 0.4, don't see anything that's not a dead short there. 0.4, going that way. The windings of the transformer are going to influence the readings, I think, on these. Yeah, we get continuity in both directions on those diodes, but probably because of the transformer. It's not a dead short, though. Yeah, it is conducting there, because when it's not in the diode mode, yeah. So that, you can see that says 1.4 megohms, almost 1.5 megohms. But when you put in the diode setting, it's able to make the diode conduct, which is why you have a diode test. You can't test a diode in the continuity or the ohms over here. It doesn't have enough voltage to make the diode forward conduct. So I'm not going to do anything with these diodes yet. I don't think there's any issue going on there. This capacitor could be suspect. Incidentally, this capacitor, we have a short over here. This capacitor is not across the AC output. This is the filter capacitor that with the voltage here, you can basically see these traces are coming down and coming over to the H bridge. To have a short over here makes me think maybe we've got a defective transistor, possibly. One or more defective transistors over here. Let's take a look. Just, geez, got a short there, short across there. Doesn't matter. It's just going through some of these pins on or pads on the back of these. Now that's interesting. So that's 21 ohms there. A little bit higher. 9K over there, so we're getting 1 ohm. Yeah, there's some very low resistance readings and a couple that are a little bit higher there, so that's suspicious. I think what I will do is pull one of these off of here. Pull one of those off of there and see exactly what happens with some readings out of the circuit. Give us a better idea if we're looking in the right spot. I'll be right back as soon as I get my desoldering gun, and we'll take a look. Okay, let's pull off one of the transistors here, desolder it, and see how it tests out a circuit. So this transistor has that little, looks like a little cover over it. You can see here, and it's that thermal, it's an insulator, but it's a thermal conductive type material. So let's see if I can get that off of there. Don't want it to tear. It's kind of stuck from being clamped down. Yeah, if you just kind of squeeze it, it's on the camera here, you kind of squeeze the side, it pops loose and it breaks the kind of the bond that it has to the body of the transistor, sort of. Okay, there it comes off. Really stuck tight on the back side there. I kind of used a little screwdriver and poked up underneath there, and it broke the seal, kind of the way it was stuck in there. It's not an adhesive or anything, but it was just stuck there, so it didn't want to just slide off. If you pull on these, it'll end up tearing the material, so try and reuse them if possible. So what do we have here for a part number? It looks like pretty hard to see on camera. I don't think that's not really going to show up there on camera. It looks like pretty faint writing on there. IR International Rectifier. Yikes, that is really hard to see. It's real faint. So the writing on this transistor is just too faint to see. I don't know if the writing got pulled off a little bit by that thermal sort of little pad thing that was over it, the cover. It's really faint on there. I can't make out the writing at all. I can see IR for International Rectifier, so we're going to have to investigate and see what that part number is. Maybe one of those others we can read. They're likely the same part number, typically, in this configuration. They're probably not complementary pairs. They would likely be all the same part number, I think. We'll find out. Let's take a reading on this transistor here and just see exactly what we have while it's out of circuit, though. Flip it over this way. Well, I think there's our problem. Yep. Thing is completely toast. Shorted. Any combination that you go across, it has a short. Wow. So there it is. That is definitely a problem. So let's see if the short circuit changed at all. Interesting. So now when we go across this main filter capacitor, the reading is in the megohms. So those others may be okay. It's got a negative. There might be some voltage on that. Yeah, there's a little bit of voltage on there. It's making it read a negative on that ohms reading there, continuity. So anyway, that looks like we might be on the right track. So let's come back over here across the AC output again. Yeah, it's giving a negative. There might be some voltage sitting on that circuit there just a little bit. Still, it's giving a really, half megohm right there. That looks really good. Definitely an improvement. Yeah, see on the voltage, there's a tiny little bit of voltage that is built up, or for whatever reason. Now that the short circuit is gone, there's just a little bit of voltage. It doesn't take much to interfere with the resistance reading. So I think replacing all four of these would probably be a wise move. If one is gone, these others may have been stressed. I don't think it's good to leave them in there you know, change one and leave the other three. So I'll go ahead and pull these out and see if I can make out a part number on there, and then I'll be back and I'll let you know what I find out. All right, I pulled the second transistor off right in this position right here, and the part number appears to be IRF640N. IRF640N. I don't know if you're going to be able to see it. The second one was a little more legible. If I get the light on it there and sort of hold it at an angle, you can make out the IRF, and at the very top, way up here at the very top edge, is where the part number is at. Pretty hard to see it. I don't think it's going to pick it up on there. But at any rate, I was able to make out IRF640N, and then the transistor that we pulled out on the first position, knowing what this one said, I was able to figure out that the first one in fact does say that same part number. Again, it's really faint. This one's even harder to see, but way at the top I can make out the 6, the 4, the 0 is really hard to see, and then you can see the N after it, so I'm certain that it is the same part number. So let's take a look at this second transistor, if it has any shorts or any issues going on, with a quick continuity test. So if we go like that. Wow, interesting. That one looks like it's shorted too. That's weird that the circuit didn't show any additional short circuits. You know, when we pulled that first one out, when we came over here across the, and look at that, see it's up in the megohm range with just the first one out, but this one here looks like it's bad too. Just any of the combinations that you go across, it's just looks like a dead short. So no question that they all need to be replaced. So I will be back when I get the final two pulled off the board. Okay, I have the final two IRF640N transistors pulled off of the circuit board. They're in these two positions over here. And I also pulled off this filter capacitor that was located right here. I was curious about something, and I'm glad that I pulled it off the board because I found an interesting surprise that we needed to take care of. Certainly for the longevity of this unit, this could have easily been the next component to go out, and you'll see why in a moment. So let's take a look at these last two and see if they are also shorted or have any suspicious readings. They'll get replaced anyways, but if we come across this one here, go, yeah, it's shorted, 1 ohm, 21 ohms, that looks pretty bad, 21 ohms there, doesn't really matter what combination, 21 ohms, so it's definitely no good. This one, the writing was much more legible, it wasn't so hard to read, and it's clearly IRF640N, so without a doubt that's what all of them are, so it was the easiest one to read. Come over here on this one. So this one actually 3.2 megohms there, but the outer leads show open, middle to the right hand shows open. Either this one failed and is completely burned open inside, or maybe it is actually good, but it tests different than all the others, but clearly will get replaced. So if we go across the circuit board where this capacitor used to be right here, you can see 121, almost 122 k ohm, and that makes sense because there's a bleeder resistor in that circuit. So there will be that resistance across there, but it's no longer that dead short that we had before. If we come across the AC output right here, going over to the outlet, it's giving that negative reading. It's probably, there's a little bit of a voltage that seems to have, keeps building up on that. But it's clearly in the megohm range, very high resistance where it was a dead short before. Come across to some of these traces over here. Everything looks like it's in the k ohm range or megohms. So it looks like the The short circuit has gone away. Those transistors looked like they were the only defective parts, so I'll get those ordered up. I don't have any IRF 640Ns on the shelf, so I'll get 4 of those ordered, and I'll be back as soon as those are in, and we'll get those installed. But let's take a look at this capacitor. So if we run a quick test on it, an ESR of 0.32 ohms, so not too bad. 229.4, almost 230 microfarad. So the actual rating on this capacitor is 220 microfarad, so we're right there within spec. 250 volts. It says KME 105C, 105C, the temperature rating. So not a bad choice for the temperature rating. I'd like to see something Nichicon or something like that in there. Might be a little bit better choice. So it's out, might as well replace it. In fact, we will replace it because, interestingly, it says 220 microfarad, 250 volt, which I would have gone with as a replacement using those numbers. But when you look at the circuit board, 450 volts, 150 microfarad, 450 volts, and they've got a 250 volt part in there. So that's, I don't know what was going on there. That doesn't seem right. Seems pretty unusual. It doesn't look like it had been replaced. You know, the solder and everything looked original. I don't think this has been changed out, but I don't know. I will try to find a 450 volt cap that can go in here that should fit. I think I can do it. You can see this diameter is smaller than the sort of the marking, the silk screen on the board. So something that's a little bit fatter in diameter. The height is restricted. We don't have a lot of room inside the unit, so I really can't go much taller, so we'll have to see what's available. 150 microfarad, this is 220 microfarad. Seems like the higher capacitance should be okay. I don't think that'll be an issue. I stay with that. But if the trade-off is that the size, if it's 220 microfarad and 450 volts, it just may physically be too big. So to get the higher voltage, maybe the capacitance will have to be a little bit less. I'll have to look and see what's available. But I don't like seeing that voltage at 250 when this said 450 here. 450, it seems actually a little bit on the high side. I mean, we have 120 volts here, and it's 120 volts RMS. The peak is higher than that, but still 220 may be a little bit on the low side. Doesn't look like it's leaked, hasn't popped the vent or anything, but we'll change it. We'll put something better in there. So I will be back when the components are in. I don't have a capacitor on the shelf here that will work in place of this, so we'll get that ordered up as well. Some new transistors, and I'll be back when the parts are here, and we'll continue on. All right, here we are several days later, and the package from Mouser Electronics has arrived, so we have the components needed to continue on with the repair. So you can see the IRF 640 N-channel MOSFET transistors, and there's 8 of them. I only need 4 for this repair. Gives me a few spares. I didn't have any of these on hand, so I don't mind having a few spares. Plus, if something unfortunate goes wrong with this repair, if there's some other defect on this board that we don't know about yet and it takes out the new transistors, it would give us some spares without having to place a whole new order, so they're not very expensive. Nice to have those on hand. Here's the new capacitor, Nichicon 105 rated, 105 degrees C rated, and you can see it's, get that over here, 220 microfarad, 400 volt. The original, again, was 250 volts at 220 microfarad, so we're keeping the capacitance the same but increasing that voltage rating. And again, on the circuit board, 450 volts was marked at 150 microfarad. So I could not find a 450 volt capacitor. Nothing of that voltage would actually fit on the circuit board. Either the leads were too far apart, or the diameter or the height, there was no combination. But the 400 volts is the closest I could find. I don't think this circuit runs anywhere near 450 volts. We'll find that out once this is powered up. We'll definitely take a reading across that and see exactly what voltage is on that capacitor. It'll be interesting to see if this capacitor that they had installed in here, was it being used, below the voltage rating, or was it somehow above that rating? They'll be interesting to find out. And also we'll want to know if this new capacitor is running, something well below 400 volts. We hope to see that. I don't want to see it running at 400 or even just, 10 volts under. I want to see a safety margin on that. So we'll find all that out once the circuit is, back to working condition. Something to keep in mind when you're working around or working with MOSFET transistors is that they're a static sensitive device. You can see this is anti-static packaging. The tape on the end is an anti-static type of tape. Just use precautions when you're handling these. Really never touch the lead when they're out of the circuit. Don't touch across them. Handle them by the tab up at the top. The reason is the gate lead on a MOSFET can build up a charge when it's out of circuit, and that charge can damage the transistor. The gate lead has a very, very high resistance. Okay, so the charge will build up and basically stay or remain on that lead and not discharge. You want to make sure to use soldering equipment that's also ESD safe or ESD approved type soldering equipment. It basically means that the tip of the soldering iron doesn't get a stray voltage buildup on it. That the tip is grounded, basically, is what that would mean. So the next thing that I will do is prepare these transistors. I need to form the leads. So here's one of the defective ones that we removed. And if you see kind of a side view, the leads have a bend that sort of comes up and bends a little bit. That causes an offset so that they sit against the heat sink. So I'll prepare the next 4, get those soldered into the board. I'll also solder in this new capacitor, and then we'll be able to power it up, or at least try to, and see what happens. And if you're following along and you're working on a power inverter like this model or something similar, just know that you do so at your own risk. When these inverters are operating, there is high voltage, 120 volts over here at the AC outlet, high voltage on this capacitor. The voltage that's in here would be no different than the danger that you would have at an outlet in your house. There's definitely some high current that would be available here, would give a nasty, if not lethal shock. So use precautions, just common sense, and you do so at your own risk when working on something like this. If you don't know the shock hazards, don't know the safety precautions and the risks that are involved, please refrain from working on something like this until you fully understand it. Just take care and be safe. So I'll be back as soon as I get the components installed in the circuit board. I have the 4 MOSFETs lightly tacked into place. You can see them down there. All right. So by lightly tacked in, I mean one lead is soldered with just a touch of solder from the top side of the board. These are plated through holes, so they take a little bit of solder. So each one has just one lead that is just lightly soldered. In just a moment, I'll pull the circuit board out of the case and complete the soldering from the back side of the board. But the reason I did this is because we want those MOSFETs to sit true and flush against the side of the case, because that acts as a heat sink. So if we look, if my hand is represents the case, we want the MOSFET to sit, flat like this, not tipped outward or, in some way twisted or not sitting flush. These clamps like this go across the MOSFET, and you can see there's a threaded hole here, so they span one MOSFET here, one MOSFET over here, and then they pull down tightly. If the MOSFET is being held by its leads and sort of standing outward, like this, and then you pull it down and force it, something over time could crack. I mean, the case could crack, it could damage the circuit board. If it never pulls the MOSFET completely down against the heat sink, you would have very poor thermal transfer, and it could lead to a failure as well. So that's something to keep in mind when you're installing transistors that must be pulled down against a heat sink, is to make sure that they can do so before you complete the soldering. Now, these little sleeves go over the MOSFET like so. All right. So it just pokes over it like that, and that acts as an electrical insulator, but it's a thermal conductive pad. So we'll slip these over when we're ready to actually install everything and put the little clamps in place. So I'll remove this and continue on with the soldering, and I'll be back. Okay, all the new components are now installed on the circuit board, so we're ready to power up the inverter and see if it functions correctly. Now, something that you may notice it has changed since the previous portion of the video is that this ribbon cable has been changed out. There's a 6-conductor ribbon cable right here. This is the original cable. You can see it's this has a heat shrink over it, but It's basically a plastic substrate that has little conductors embedded into it. And you can see right here, these are the sockets that went on the end. So this was soldered onto the board. There's little tiny pins, very small. And it's basically a friction fit. This just sort of plugs in like so. So, like that. Well, they're pretty fragile. There was a lot of flexing. This was really bending around quite a bit while I was working on this and replacing these components. You know, this end piece out here was moving around quite a bit. And I noticed that on one end of this flexible cable, it looked like something had come out of position, and I looked a little bit closer, and one of the traces looked like it had lifted up off of the end and basically had broken, so that was not going to work. Really no way to repair one of these on the end. There's just nothing you can do, and I don't have any spare, pieces of this material or these cables. So I thought, well, the simplest way will be to just replace the 6 conductors in here with 6 individual wires. So that's what this ribbon cable is over here. So I just followed, which end here and which pin it went to the appropriate pin on the other end, from one end to the other. Made those connections over here. So that is taken care of and should not cause any trouble at all now. This will actually be a little bit stronger and a better connection. These ribbon cables like this, these ends are not, it's a friction fit. They're not the most rugged. Some vibration, something could come loose, so I don't mind having something like this in here anyways. That's a really better design. There's also no reason that this needs to plug together. When this assembles back in the case, which is off camera, this stays together. You're not unplugging anything, so it won't be any issue to have this permanently soldered together like it is. So let me get the power supply hooked up and let's see if this functions. Now for this test, I have a power supply that's rated 5 amps and these light duty test leads, jumper wires if you want to call them, from the power supply with the alligator clips on the end. And it'll be fine to test this. It draws very little current, idling, no load condition. When this is under load, it can draw, I think, upwards of about 30 amps. So to test this under load, which we'll do if it actually functions for this test, I have a larger power supply over there, and we'll hook that up to power this under the full load. So we'll come in here and make this connection here, positive over here. So I'll set the power supply to 12 volts. Right about there, 12 or 12 and a half. Let's take a look here. The voltmeter, get this positioned. I think you can see this a little bit better. It's some glare on the screen there. Yeah, like so. Okay. So let's just confirm we have our voltage here. Yep. Looks good. 12.4, no problems with that. So I'll put this on AC volts and let's see if the inverter works. So we'll turn it on. All right, so we get a momentary beep, and although you cannot see it on the camera, I don't know if I can lift this up, but the green light is on. I think this will turn here. Yep, there you can see over there. So there's a red and a green LED. The red indicator is a problem or a fault, typically overload or over temperature or something like that. And the green, of course, is the power. So this appears to be powered up. Let's take a reading on the AC outlet and see what voltage we have there. And hopefully it's very close to 120 volts. No problems there. So 120.9, 121. 120.7, right in there. So that looks very good. So my power supply is showing 0.4 amps right now as a current draw for the inverter. So again, very low current when it's not under load. Let's take a look at the frequency on the output. Should be 60 hertz or very close to that. So we'll set this to frequency. Take a look here. Yeah, that looks very good. So 60.24 hertz. So again, 60 would be ideal, and 60.24, nothing wrong with that. That would certainly power any device that you would connect to this with no trouble. So technically, if you had a clock with a motor in it that the motor speed varies with the frequency, old style mechanical clock with an AC motor in them, with this, it would run just a little bit fast because this frequency is just a little bit above 60 hertz. But for any modern device like a cell phone charger or a laptop computer, something like that, where this is just powering basically maybe a battery charger or a power supply or something like that, a slight variation in the frequency is not a problem whatsoever. So looking very good. So the inverter is working well. It looks like those 4 transistors took care of the problem. Now, I had mentioned this capacitor was changed out to this new type with a higher voltage rating. Let's take a reading on this capacitor and see what voltage is actually on that capacitor. So we need to be careful because now this is operating. There's 120 volts over here, and I need to reposition this so we can get underneath here. I think that should work right like that. That'll stay. So that capacitor is right on these 2 traces here. So let's take a reading. So interesting. So we have 204.2 volts. 204, yeah, right at 204. And that's DC, okay? So 204 volts DC. So this original capacitor actually was okay. Again, it was 250 volts. This capacitor, I tested it and it does check out okay. There's nothing wrong with it. So now I have a suspicion that the marking on the circuit board was in fact the higher voltage rating because this inverter was likely available in a 240 volt 50 hertz configuration for use in countries where that's a standard line voltage. In the United States, 120 volts at 60 hertz is a standard wall outlet voltage or line voltage. But in other countries, 240 volts at 50 hertz is commonly used, and so this could likely be configured for those applications. They would just have a different outlet configured over here. If this was putting out 240 volts, that would be a factory configuration. There's nothing I can do now that you would be changing this. But if this was produced at the factory to make 240 volts AC on the outlet, you would certainly have a higher voltage on that capacitor, probably well into that 300 and some volts, approaching 400 or whatever, and the 450 volt capacitor would likely be needed, or something at least around 400 volts, maybe higher. So that's probably why they had that marking on there, and then in this configuration it can withstand having that smaller or lower value capacitor. The capacitor that I chose is 400 volts, and it certainly won't have any issues in there. It's basically running at half the rated voltage, so no problems with that. Now, something that I had noticed on this inverter when I took it apart, there's a sensor here. It may be a little bit hard to see, and what I will do is zoom in a little bit closer here. The inverter's turned off right now. Get that. So this sensor right here, this pointer right here. There's a little, well, I think it's a sensor. It's covered in heat shrink, and it has a lead coming up and looping and goes down, just makes kind of a U shape right here. Appears to be a component, but it's covered with heat shrink right here. My suspicion is that this is some type of a temperature sensor, and something that I would like to know is that if this fan runs correctly. Now, we had a failure where transistors were damaged, the MOSFETs were damaged, and over temperature could certainly be a cause of that. So it'd be nice to know if this fan is able to turn on correctly. And what I noticed when I took this apart and out of the case, this temperature sensor was not touching the heatsink. Although it's very close right here, I've actually bent it outward a little bit. It was basically just kind of hanging out right around in here, not touching the heatsink whatsoever. So the ambient air temperature in here is not what you're trying to sense. You want to know what the heatsink temperature is. Well, it certainly wasn't touching the heatsink, and if this couldn't sense the temperature, this fan may not have been kicking on soon enough, or ever for that matter. So I'm just curious if this actually is the temperature sensor. So I'm going to touch it just briefly with the soldering iron. I'll just bring the tip of the soldering iron just close to it and heat it up a little bit, and let's see if this fan turns on. The inverter's turned back on again. Grab my soldering iron, The beep you hear is just this coming up to temperature. All right, so this is 725 degrees right now, and we'll just get it near the sensor right here, and let's just see if that causes that fan to turn on. And it does. It in fact does turn on. You may be able to hear that. Okay, and it just turned off. So that's good to see. So this does control the fan, and I'll make sure that when this is reassembled that this sensor has a thermal compound and is making a good connection over to the side of the heatsink. This is a pure sine wave power inverter, or a true sine wave output. So let's take a look at the waveform on the oscilloscope and see that it has no distortion, and that the waveform does in fact look like a true sine wave. So I have 12 volts applied to the power inverter, again from the power supply like we previously used. So I'll go ahead and turn the inverter on. Now I should point out, in this setup here we have the oscilloscope connected over to the AC outlet. You do not want to make a connection like this with a traditional scope that has a grounded chassis, okay? This oscilloscope is battery powered and the chassis is completely insulated. There is no parts on the front panel or anywhere that you can get a shock from. So the ground lead on the probe over here goes to an internal ground connection within the scope, but it poses no shock hazard. And again, this is not plugged into an AC outlet, so there's no short circuit danger. If you use a traditional scope that has a grounded chassis and you connect this to a traditional AC outlet, very bad things can happen. You can end up with a short circuit or a shock hazard on the oscilloscope. So again, this configuration that you see here is only safe to do when you have an oscilloscope like this that is basically floating or isolated. So keep that in mind. And again, if you're doing any work like this with an oscilloscope, you do so at your own risk. So we can see we do in fact have a waveform. All right, so let's make a couple adjustments on the scope, make that a little bit better to see, a little easier to see on there. That a little bit taller. That's a little bit too much, we'll go down like that. Change the sweep time here. One more like that. All right, so that's looking very good. I'll move the camera over and zoom in a little bit here so you can see that a little easier. See if I can brighten that up, pardon the camera bumping there. All right, I think you can see the graticules on there. So what we have is 100 volts per division on the graticules for the vertical deflection, and the horizontal sweep time is set to 5 milliseconds, okay, per graticule, so 5 milliseconds per division. This number over here is just the trigger level voltage, which is currently at 1.42. If that's changed like so, that's just the trigger point on the waveform. What I can do is place the trough right there, like that, that'll be fine. So that waveform is looking very good, no issues with that. It looks like there's equal deflection or amplitude above and below the center ground reference. So if I turn the inverter off again, you can see this represents ground right in the center on the trace there with no signal. So we want to see an equal amplitude above and below that. So I'll turn the power inverter back on again. There we go. And we do in fact have an equal amount above and below that ground reference, so that looks very good. Looks like a stable waveform, no distortion. So that's looking very good, no issues with that whatsoever. So the power inverter, the last test that we need to do is a full power test, and I'll do that once it's back in the case, because right now without the case there's no heat sink. The transistors would quickly overheat. It needs to be installed in the housing or in the case before we can do any kind of load test on it. So that'll be the next thing that I do. Let me move the camera back over here one other thing, pardon the movement here. I'm going to zoom back out just a little bit here. So on this side over here, there is a convenience USB port, for charging cell phones or small devices like that. So this is a voltmeter, and it actually has an amp meter built in to show current draw and voltage on a USB port. So if you plug a USB device in here, and of course the source is right here and there's two USB ports on it, it will show you the current draw through that to those devices. It will also show you the voltage that's being supplied. Well, I don't have a USB device to plug into here, but we do want to see that this is producing the 5 volts. So we won't have a current indication, but we'll have voltage. So let's see if in fact we do have 5 volts over here. So plug this in here. Again, there is 120 volts on this, so I want to be very careful with that. That in. Of course, the position here, it's turned a little bit, it's upside down, but so you're actually looking at this, that's 5.11 it looks like, 5.17. Pardon the upside down display, but we do have the correct voltage over there. That looks fine, no issues with that. So it means that the 5 volt power supply on the board is functioning correctly, so that's good to see. And again, the zeros here is the current draw if we had a USB device that was actually plugged into here. I believe this USB output on here is rated 2 amps. I think that's the rating. I'm not sure, I'd have to double check the spec sheet, but I think it's 2 amps. So that's looking very good, no issues with that. So I'll go ahead and get things put back together again, and I'll be back as soon as it's reassembled. Okay, the power inverter is now completely reassembled, so let's try a full load test on it and see how it performs. So the inverter is rated at 300 watts maximum output, and I have a 300 watt incandescent lamp over here. It's plugged into the AC outlet on the inverter, and you can hear it running over on that side. You can see the power wires coming in right here on these alligator clips, and over there is my power supply that is set for 14 volts. The inverter is rated to operate from 12 to 15 volts, so typical voltages in an automotive application. There's a 30 amp fuse, it's right on the side of the inverter, and my power supply can supply in excess of 30 amps, so any current demands that the inverter will have will not be a problem. Power supply will keep up with that. And I have the oscilloscope over here, and it is set, or the probe is connected across the AC line at the base of the lamp. That way we can monitor the waveform on the output of the inverter under full load. We want to make sure that it continues to put out that sine wave that we saw under no load. So we'll watch that as well. Now when the lamp turns on, it's going to be very bright. Again, it's 300 watts. So I'm not sure how the camera will do when that turns on. It may kind of wash out. I don't know if we'll be able to see the scope or not. I might have to zoom in just on the scope because that lamp may be quite bright, and it'll probably wash out pretty much the picture, so we'll see what happens. All right, everything is set up. Let's try it out. Not bad. Not bad at all. So now you can still see the oscilloscope screen, so no problems there. So the inverter is actually drawing a little over 20 amps, it looks like. Maybe 22 amps or so. Best I can tell from here, the power supply is across the bench over there, but it looks like a little over 20 amps. So the waveform looks really good, no issues with that. I'll zoom the camera in here. You can see that, that looks really good. Make an adjustment here. All right. So under full load, it looks really good. No problems whatsoever with that. All right, it looks like this was a successful repair. The inverter is back in business and ready to be put to use. Here's the power inverter operating with a 100 watt incandescent lamp. I also tried a 150 and 200 watt incandescent lamp. and it's functioned very well under any of the different loads that I've connected. So at this point, the inverter is ready to put back into service. The repairs have been successful. The output sine wave has looked very stable, no distortion or any issues with that as well. So looking very good at this point. If you enjoyed this video, don't forget to give a thumbs up. And if you're enjoying the videos on this channel, don't forget to subscribe. So until next time, take care and goodbye.